Many of us became interested in astronomy because of the majesties of the universe. But many of us got interested in physics because we wanted to understand the mechanisms behind those majesties, to see basically the gears of the universe itself. And that's what attracts us to things like neutrino astronomy and gravitational wave astronomy. They have the potential to reveal the inner workings of things and to reveal things that electromagnetic observations cannot. So as I showed before, there's 3 different ways we could try to detect supernova neutrinos, and ultimately we need to use all 3 of them. And they're sensitive to different things. So, for a nearby Milky Way burst, we would have very high statistics, so we could measure the spectra very well. We could measure the time profiles, aka the light curves, very well. And we would be able to measure all the different neutrino flavors. This is the thing that is closest to what we can do in the electromagnetic spectrum, electromagnetic bands, to have a complete characterization of the event. But the problem is that the supernova rate in the Milky Way is probably maybe 2 per century. What can we do while we're waiting for that to happen? We've been waiting a long time, but nature will favor us eventually. One of the things I'm going to spend the most time on today is the diffuse supernova neutrino background, which is the flux of the neutrinos from all the core collapses that ever happened in the history of the universe. That flux is a steady isotropic flux that's with us all the time. We could detect it anytime if we have sensitive enough detectors. Now, that will not give us anything about the time profiles of individual events, and it will only let us detect probably 1 flavor, electron antineutrinos. But it does have the potential to let us measure the spectrum of the average core collapse. That means averaged over stellar progenitor masses. That means averaged over neutron star outcomes and black hole outcomes. And that would be a very powerful tool for comparing to supernova 1987A data, for example, or 2025 GW data. We expect that the neutrino emission from core collapse supernovae is quite similar from one core collapse to the next, but that needs to be tested. By the way, that is in contrast with the electromagnetic emission from core collapses, which varies wildly between different objects. And the reason is the electromagnetic emission from the envelope, of course, depends on the stellar mass. Smaller or larger progenitor could obviously be different, but also through how the shock propagates through that and how energized the shock is. So it's not surprising that the optical displays of core collapse supernovae vary a lot. But because the neutrino emission comes from the formation of a protoneutron star, and we think that neutron stars have fairly uniform properties, there's great uniformity at lowest order expected in the neutrino emission from different core collapses. But we want to test that. And of course, this will do it. Eventually, we also want to detect supernovae from nearby galaxies. And this will only ever be like maybe a few events at a time. But this will also allow us to construct the average spectrum from core collapse. And it will also help us detect potentially differences between different kinds of core collapse. I'll say more about all of this. This slide is basically an outline of the talk. Okay, so in the first lecture, we covered basics. And in the second lecture, we're going to cover detection in these 3 domains: Milky Way, nearby galaxies, and the DSB. And as before, I'm focusing my attention on providing a conceptual framework for people who are new to neutrino astronomy. Lots and lots of details I'm leaving out. But I want everybody to walk away with an idea of what the big picture is, and also what kinds of things they could look up if they wanted to learn more. So let's start with the Milky Way. And we already talked about this, that, the idea is that you form a protoneutron star and that the change in gravitational potential energy is carried away by neutrinos because only neutrinos could do the job. And that this energy is huge. In one set of units, it's 3 times 10 to the 53 erg, 10% of a solar mass mc squared. And in other units, it's something like 10 to the 59 MeV. Truly staggering number. And so the number of neutrinos, by the way, is about 10 to the 58 emitted neutrinos. And the neutrinos dominate the energy. As Tony mentioned earlier, the kinetic energy of the shock might be 10 to the 51 erg. And the electromagnetic display I mentioned earlier is even smaller than that, maybe 10 to the 49 erg. So in physics problems, well, in political problems, the old adage is follow the money to figure things out. In physics problems, we follow the energy. And the reason that we're so attracted to measuring the neutrinos is not only the fact that they can reveal the deep interior of the supernova, but it's mainly because the neutrinos are connected to the mechanism of the explosion itself. The neutrinos directly connect to what powers the core collapse. So follow the energy. Now, really, this has to be done in great detail in multi-dimensional, it's like 2D, 3D simulations, like those carried out by Tony Mezzacapa's group at Oak Ridge. And you can see that this picture on the right is much more complex than the simple thing I've been drawing on the left. Now, one of the things that we would like to know is, can we learn something new from 87A? So a couple of years ago, my collaborators and I looked into this. And what we did is we looked up the predictions. We focused on the first 1 second of neutrino data. And we took every supernova simulation we could find, or at least all the contemporary ones, 1D, 2D, and 3D, and we plotted their predictions in the bottom left. So there you see the neutrino luminosity versus time, and you see the neutrino average energy versus time. And you see right away that there's a lot of similarity between the models. There are a couple of exceptions, but generally speaking, the models fall in a pretty tight band. And I think that is a testament to the decades of hard work that the supernova modelers have put into this. These are incredibly complicated simulations involving not just, hydrodynamics, but general relativity and extremely difficult numerical calculations. So it's like I said, it's a testament that they agree. And the interesting thing here is we did not restrict these models to all have the same progenitors. We did not restrict them to all have the same nuclear equations of state. We didn't do anything. We just took everything published for every scenario, all of the different inputs. We didn't condition on that at all and just plotted them on the page and see what happens. So this is like the worst that could happen. If we compared these simulations for the same inputs, they would surely agree even better. So during the first, fraction of 1 second, when the neutrino emission is the brightest, it's remarkable how well they agree. Now, what's interesting is they disagree with the data, and that's shown on the bottom right. And one way you can check this is the number of counts and the average energy of those counts in the first fraction of a second. Here we used half a second because not all of the simulations went out to 1 second. Later, when more simulations go for later time, this exercise can be repeated. By the way, you notice in the figure on the bottom left that a lot of the simulations cut off. And that's simply due to the computational costs. And over time, we expect that more and more simulations will run at higher and higher fidelity to later and later times. And as that happens, they will be able to make more and more detailed comparisons to the supernova 1987A data. And you might think, well, that data is only 20 events. How good could it be? Well, it's good enough, actually. And the models can be quite different in their late time predictions, even though they're pretty similar in their early time predictions. And so this will get more and more interesting as time goes on. Anyway, what you can see is in the bottom left there that the data, the number of counts observed is significantly smaller than predicted, and the average energy of those counts is significantly smaller than predicted. So what that means is, oh, sorry, I said that wrong. That's for Kamioka. For IMB, it's a little bit different. Those are the two different detectors. So what does this mean? It means that the true supernova luminosities and or the average energies were probably a little bit lower than predicted in models. And figuring this out is a very important problem. Now, after our paper came out, another group wrote a follow-up paper where they considered mostly the later time evolution. And they also criticized our work. And they had several criticisms, but I want to show you how easy it is to defeat one of those. Their main criticism was that the models actually agree with the data. And what we show in the bottom right here, these two panels, everything you see in blue is what's on the far bottom left in our original paper. And then what we added in, I think that's gold or orange or something, is the models that they used in their paper. And so we used the 1D, 2D, and 3D models. So the 2D and 3D models, many of them explode on their own. The 1D models generally do not, and explosions have to be forced in an artificial way. 1D just means spherically symmetric. So in their paper, they used these 1D models that are shown here in this, like I said, orange or gold color. And you'll notice that those are far below the predictions of the 2D and 3D models, which are much more realistic. And you'll also notice that those 1D models that they used all have extremely sharp cutoffs. And that's where they make a cut to excise part of the region and force an explosion that doesn't happen naturally. So it's no surprise that these models that have, I would say, artificially low temperature, luminosities and artificially low average energies are in better agreement with 87A data. But they're not in agreement with the most sophisticated 2D and 3D simulations, including by the authors of that work itself. Okay, so what are we going to get for the yields from a Milky Way burst? I talked about this before, so I'm just going to flash it again. We have the potential to get up to 10,000 events in total from a variety of detectors. Super K is running now. Juno will be soon, and Dune will come later, and IceCube is running now. And I emphasized earlier that one reason it's important to have multiple detectors is we want to make sure that, maybe somebody didn't turn off their detector for the day or something like that. But more important than that is different detectors have different capabilities. And it's incredibly important to reconstruct all of the flavors. And I'm going to remind you that it's possible to identify the electron neutrino flavor through the way they interact with nuclei, like in argon. It's possible to identify the anti-electron or nu bar flavor through how they interact with protons. They make a positron and a neutron. And the other flavors, nu mu, nu tau, and their antiparticles, is collectively called nu x. And we think that their emission is basically identical among those four. So what that means is we really can think of supernova neutrinos as having kind of three flavors, nu bar, and nu x. But the only way to reconstruct the total energy emitted by the supernova, and more important, the only way to see the differences between the flavors is to detect all of them. So how are we actually going to find the supernova if it happens in the Milky Way? I mean, like find it on the sky. And so this is in a paper I wrote quite a long time ago. Can a supernova be located by its neutrinos? And the answer is yes, by neutrino electron scattering. Because the neutrinos have energies of like tens of MeV, much bigger than the electron mass, then the electrons are scattered very forward. And the electrons are scattered within some, like, let's say, several degrees. That is smeared somewhat by detector effects, but collectively, from the statistical power of many events in the forward direction, Super Kamiokande, for example, could reconstruct the neutrino direction to of order 1 degree. This is fantastically good by neutrino astronomy standards. It's not that great by optical astronomy standards, but being able to restrict where the supernova is in the sky to a degree or a few degrees is a remarkable possibility. And it'll be very important to helping us figure out what's going on. One thing I didn't mention earlier, I should have mentioned, came in the Zoom questions. The neutrinos are emitted from the protoneutron star promptly, right at collapse. And any gravitational wave signal would also be emitted then. Once the shock is launched, the shock travels less than the speed of light through the envelope, and then therefore breaking out of the envelope takes time. Like in the case of 87A, the neutrinos arrived a few hours before the first electromagnetic signals. And that's again just because the neutrinos leave promptly, and then it takes some time for the shock to propagate through the envelope and bust it out. At the time of this paper in the upper left, there was a lot of speculation about trying to figure out where in the sky a supernova was by so-called triangulation, where basically, let's say, this detector sees it first and this detector sees it second, then that tells you that the supernova was somewhere over there. This is a very familiar technique if you work in gravitational waves. But we showed in that paper that it is not possible to do this. And the reason is that the supernova signal is too broad in time to be able to act. The supernova signal basically lasts 10 seconds. The Earth is only 40 milliseconds across. Of course, you can use features in the neutrino time profile to shorten the relevant time scale, but it's still incredibly difficult. Basically, the Earth is too small and the supernova neutrino signal is too long. So this is not going to happen. In the past couple of years, a few people have written papers saying that they think it could happen. I am quite confident that it cannot. So that's a start. Then what do we do next? Well, you've probably heard of SNOOS, the Supernova Early Warning System. And what SNOOS does is collects the signals from many detectors and makes sure that it's a real signal and not some weird glitch in one detector. Unfortunately, SNOOS does not provide directionality because the only detector that has the directionality capabilities is Super Kamiokande, and they plan to announce that on their own. But SNOOS would be great for confirming the fact of a supernova. One of the other things we want to do is find it in the electromagnetic, and one of the ways to do that is the all-sky automated survey for supernovae. And this is based out of Ohio State. Some of you may recognize this name. this is a successor of a previous observatory that we collaborated with and then superseded, the All-Sky Automated Survey, started in Warsaw by Grzegorz Permansky. And what this does is it scans the entire sky multiple times every night and looks for difference imaging to see if something brightens. So this will be important for finding the optical supernova as soon as possible in the sky, and then allowing larger telescopes to follow up in more detail. The other thing we want to do is put this in a multi-messenger framework. Don't have time to talk about that today, but these two papers here will be helpful to you in understanding how to do that. Okay, that's the Milky Way picture. That's kind of the easy part. Now, from all of that data, we would hope to reconstruct the energy spectra, the time profiles, the flavors, all of that stuff. There's a lot of detail there, more than we have time for in this introductory lecture. So I'm going to keep moving and talk about what about nearby galaxies, because I get this question a lot. So let's make a simple estimate. In the Milky Way, nominal distance of 10 kiloparsecs, Super K would observe something like 10 to the 4 events. During that very short time period, we can ignore detector backgrounds, and Super K can detect even optically dark bursts. So if a core collapse leads to a black hole, and there's a huge burst of neutrinos, but no electromagnetic signal at all, Super K can still detect it and figure out its direction within a few degrees. Of course, knowing the direction doesn't really help if there's no electromagnetic signal, but it's interesting anyway. So what about something farther away? So for Andromeda, let's use round numbers. It's really a little bit closer than this. Let's pretend it's 1,000 megaparsecs. Sorry, 1,000 kiloparsecs. That's a typo. 1,000 kiloparsecs, so 100 times farther away. Then the signal would be 10,000 times smaller, or we would expect one event from Andromeda in Super K. Now, with only one event, the detector backgrounds become pretty important, and we would have to have an optical signal to figure out when to look. And earlier I mentioned that for this detection reaction, Newey boron-free protons, the signal is basically isotropic, so we don't have directionality to help us. But with larger detectors than Super K, for example, Hyper K or even something bigger, there's some possibility of being able to detect either one neutrino in coincidence with an optical signal, or maybe two neutrinos, or maybe three or more. And we pioneered this idea about 20 years ago. Even Hyper K is not really big enough to do this for more than just some of the very nearest galaxies. And by the way, I think there was a question in the chat about KM3Net. KM3Net, like IceCube, would be able to tell that a supernova occurred, but would not be able to help with the direction. So even something like Hyper K is not really big enough to see, robustly see what's happening in nearby galaxies. So we need something even bigger that doesn't exist yet. And it's attractive as a target because the core collapse rate in nearby galaxies, let's say out to 10 megaparsecs, the core collapse rate is like 1 per year. So what if we could get, a couple neutrinos from each one of those? Then, in time, you could easily build up a sample that is comparable to that of 87A. And even more exciting is in that range, there are a variety of things happening. So if a core collapse leads to something that is neutrino bright and optically bright, that's a successful core collapse supernova. If it's neutrino bright but optically dim, that's a, quote, failed supernova that makes a black hole. Those are the things that we've already talked about. But it's also possible that you could have something that's neutrino dim but optically bright. And one possibility is a type 1A or thermonuclear supernova. Another possibility is a thing called a supernova imposter. It looks like a supernova optically, but there's actually no neutrinos emitted and the star is not destroyed. And then, of course, all the time, there's, novae and other things that don't really make that much in the optical or the neutrinos. By the way, one thing people may ask about is neutron star mergers. And those make a signal that is comparable to a core collapse supernova, but they're much, much more rare, as you know from LIGO, LIGO Virgo Kagra, that they're very, very rare. And we should be so lucky to have one that's nearby. So in order to get, we need something maybe even 10 times bigger than hypercamiocondae. One possibility is sketched on the left. This is a kind of a fantasy idea of maybe something that's like 5 megatons in scale. And the idea is that if you wanted to have a passive detector for supernovae in nearby galaxies, you don't have to have all of the shielding and the precision that you need for solar neutrinos. You could do things more crudely, and therefore you would not need the cleanest water on Earth, but you could probably deploy in a lake or an ocean or something like that. And what you would like to do is get to a detector that is big enough that you see, several events, several neutrinos from one supernova. And that's shown in the bottom left. That would be very, very exciting, because then if astronomers see something bright in the optical, we can say if we saw neutrinos or not. If we see neutrinos and they don't see something in the optical, that's interesting too. This is the kind of thing we would need to be able to see neutrinos from the galaxy I showed on the very first slide of the first lecture, 2023 IXF, or even to look for neutron star mergers. We would need something even bigger. Now, for a long time, this seemed like a fantasy, but then some of our friends on IceCube pointed out that there's a possibility that they might be able to do something in the future. Now, I have to distinguish something here. On the left, I'm talking about detecting multiple neutrinos from the same core collapse. On the right is a technical detail about how many photons are detected in the PMTs, photomultiplier tubes, from one neutrino interaction. In a detector like supercamiocondae, one neutrino comes in, makes a flash of light, and that might hit like 50 PMTs. In IceCube, because of their very high noise rates, they don't get that. Basically, each neutrino event would hit at most 1 PMT. There's just not very many PMTs, or they're very far apart, more accurately. And so one thing that could happen in IceCube, if you had a dense collection of PMTs, you might have one neutrino event that can hit 2 or 3 or more PMTs at once. That would greatly reduce the backgrounds, because the noise rate in IceCube is dominated by things that hit 1 PMT at a time. And this also is being explored in KM3Net. And one of the reasons it's so interesting is both IceCube and KM3Net and other considered neutrino telescopes are, instead of having like one big PMT in a glass sphere, they're talking about having many, many, many small PMTs in a glass sphere. And that has great potential for beating down the backgrounds from thermal noise in individual PMTs. So someday it may be possible to reliably detect neutrinos from nearby galaxies. But let's move on to the diffuse supernova neutrino background, which is the thing that's closest to our reach. So in 2002, I got together with my friend Mark Vagans, who's a supercamiocondae experimentalist, and we said, we must detect the DSNV. We didn't know how, but we knew that it was important. Because after supernova 1987A, we were tired of waiting for more supernova neutrinos. And like they say, everybody complains about the weather, but nobody does anything about it. This is a way to do something about it. Let's find neutrinos sooner. So Super K has tried to do this. And here's an example of the spectrum they've observed in the detector. And what I want to tell you right away is it's all backgrounds. There's no signal in this figure. And this is because the detector backgrounds are too large, or at least they were so far. And you'll also notice that the spectrum starts at about 18 MeV. And that's because below 18 MeV, the backgrounds go whoosh up to very, very large values. So what's shown here in this big bump is a kind of detector background made by atmospheric neutrinos. And this ramp is also another background made by atmospheric neutrinos. So that's, in a way, this is good news. This is really a very small number of events compared to everything that happens in Super Kamiokande all the time. They've been able to cut away almost all of the backgrounds. I mean, the muon rate in Super Kamiokande is 2 per second. And here we're talking about, small numbers of events per year. So they cut away most of the backgrounds, and the only ones that remain are those made by neutrinos. Now, the signal is shown here, and I think this is cyan, this is the maximum possible signal allowed by this data. So this is encouraging. It gets pretty close to realistic supernova models, but it's not yet a detection. And so in order to do better, we have to beat down these backgrounds, and we have to beat down the backgrounds that are not shown off to the left, so that we can go to lower energies, because the supernova signal would be coming in from low energies, and it's bigger at low energies and it falls off. So we need to lower the threshold and kill the backgrounds. And so what Mark and I came up with is a way to do that. And here's the very short answer is the first thing you need for an ambitious project is you need a cool code name. And our code name was Gadzooks with an exclamation mark. And that stands for Gadolinium Antineutrino Detector, zealously outperforming old Kamiokande, super, exclamation mark. And the idea is that we would add a gadolinium salt to dissolve in the water of Super K. And through some magic that I'm about to explain, that allows us to beat down the backgrounds and better identify the signals. Now, I should remark that the Super K water was the purest water on Earth. It's a multi-$100 million detector. It took a long time to make, and that water is super purified. And the idea of shoveling in, 50 or 100 tons of some weird lanthanide salt was met with some skepticism and a need to do a lot of R&D. And that was done, and ultimately was passed, and the gadolinium was added to the detector. So I'm going to come back to that in a minute, but let's come back to the signal. The thing we're trying to detect is this ambient flux of neutrinos from all previous supernovae. So the thing we want is the signal rate spectrum in the detector. And the thing that we're trying to find out fundamentally is the neutrino spectrum, the average time integrated progenitor averaged neutrino spectrum from all core collapses in the universe. What is the average spectrum per core collapse? There's some redshift factors in here because many of the supernovae are at cosmological distances. This is the thing we want to find out. This is the thing that only neutrino physicists can find out. So one of the ingredients you need is the core collapse rate of the universe. And this can be measured either directly from supernovae or can be predicted from the star formation rate. This is the job of astronomers, and this can be measured with quite good precision by electromagnetic means. This is not the point of measuring the DSMB. The second ingredient here can be done by astronomers and should be done by astronomers. The first ingredient can only be done by neutrino physicists. And the third part is understanding the detector. So the cosmology part, that's all solved. We know the parameters. Oscillations, as I remarked already, are included because they happen in the supernova itself. So comparing supernovae at different distances is just a 1/4πr² factor. And detector backgrounds I'm about to talk about. So the first ingredient we need is the neutrino spectrum per core collapse. And I already told you it's about 3 × 10⁵ ergs. It's semi-equally shared among the 6 flavors of neutrinos, counting antiparticles. They have typical energies of about 15 MeV, and neutrino mixing is definitely important, but it's already included in the data, and it's already included in 87A, so we want to compare data to data. So our goal is to find that. Now, why is the spectrum so important? Just to reemphasize that, we did measure it from 87A. We hope to measure it from Supernova 2025 GW, and we will measure it from the DSNB, and it's exactly what's predicted by supernova simulations. This is a really, really key ingredient for understanding how core collapses work. Now, the second ingredient, the cosmic supernova rate, I'm going to go faster over this, but basically this can be predicted from the star formation rate, and it can be measured from the supernova rate, the optically bright supernova rate, and then also you have to take into account the so-called dark supernova rate, where core collapses lead to black holes. And work that we began at Ohio State and continued by my colleagues there are now some candidate events where a massive star is seen in the image, seen in the image, seen in the image, and then it's not seen in the image anymore. It looks like a massive star simply disappeared. And those are candidate events for dark collapses. We think that probably is about 20% of core collapses are dark, maybe more. And there's some discrepancies. This is an old picture, but it gives you an idea. There's some discrepancies in the measured supernova rate, that's the optically bright ones, compared to the prediction from the cosmic star formation rate. And at the time of this paper, it was a factor of 2. And we think that some of this was due to dark collapses, and we think some of it was due to supernovae that were missed in optical surveys. And this work continues. Okay, the third ingredient is the detector capabilities. So Super K is the big one, and it can detect Nui bar interacting with free protons, makes a positron that's easy to see, it makes a Cherenkov flash, and it always produces a neutron. Now, in regular super Kamiokande, that neutron captures on a proton and leads to an invisible signal. But if you add gadolinium, the neutron will capture on the gadolinium and it leads to a visible signal. So if you see a positron and then shortly thereafter you see a neutron, then you know that this reaction occurred. So the signal makes a positron and a neutron, but the backgrounds don't, mostly. And so that's the basic idea of this proposal, is with the gadolinium, you can detect the neutron. Without it, it's very, very hard. And what this should do is eliminate almost all of the backgrounds. Here's our original figure. And ideally, what should happen is it should allow us to lower the threshold energy of the search from like 20 MeV down to about 10. And there's more signal and less background down there. So there should be an open shot for going after the signal. So as I remarked, Super K is now operating with gadolinium and trying to realize this dream. This shows from several years ago our predictions for different simple models and how close they are to the limits. I just want you to see the thing on the right, that this band shows something what Super K had already excluded 20-something years ago before gadolinium. And these models are simple, different thermal models where the bands indicate the astrophysical uncertainties. Over time, those astrophysical uncertainties on the core collapse rate will shrink and shrink and shrink. And so we have a potential, just look at the tail of these models is much, much smaller than the tail of those models. And so even a very small number of detections can be very powerful for telling things apart, because the supernova neutrino spectrum has an exponential tail. So you are exponentially sensitive to the average energy. So this shows where we were, many years ago. This shows where we are now. This is a talk from Neutrino 2024. This is a talk by Super K. And there's a lot of details here, but I want you to see that the backgrounds are smaller. They've gone to much lower energies in the search. And I want you to notice this thing in the upper right, that they do set a limit on the DSMB flux, but look, the best fit is non-zero. They're starting to see hints of a signal. It's only a 2.3 sigma excess, but that's how excesses begin. They start small. And so to be conservative, Super K turns this into a limit, but the best fit is non-zero. And I also want you to notice that they say here that the 1,000 days of Super K with gadolinium is already equal to the previous 6,000 days without. So this is exciting. This indicates that Super K has a real chance to detect the DSMB for the very first time and to whet the appetite of hypercamiocondae to do it with higher statistics. DSMB is very important, not only for measuring the spectrum, but for just helping us see a new neutrino source for the adding to that list that I showed at the beginning of the first talk. Adding gadolinium is also important for a variety of other physics searches. In the interest of time, I'll skip that, but it's basically all winning. Okay, so to come to my closing message, we're never going to understand core collapse supernovae unless we understand the neutrinos. And in order to understand the neutrinos, we need to put that in a broader context with electromagnetic and gravitational wave observations, and also early, during, and after observations. And this is only with this combined approach do we have a chance to solve one of the most complex problems in the universe. Thank you.
Thank you, John. Magnificent. Any questions? Yeah. Hiroki?
Okay, so thank you so much for nice talk. So can you go back to the slide for comparing the 1987A and the theoretical models?
Yeah.
So in this plot, now it's a bundle of the multi-dimensional model, like, and then, oh yeah, this one. So if we rely on the Kamiokande 2, so theoretical model has a higher average energy. So, but in the IMB data, this is lower. So it looks like there are no self-consistent solutions to reconstruct for both observation data. So can you tell us how our theorists try to figure out this problem?
Yeah, that's a great question. Thank you. There is a long-standing discrepancy between the Kamioka and IMB2 data. This is still not really understood in I'm going to skip to another paper. Let's see. Where is that? Yeah, there we go. In this paper, we show how one way to think about that is that Kamioka was mostly sensitive at relatively low energies, and IMB was more sensitive at high energies. And that had to do with the detector thresholds. And so when we do a direct reconstruction of that data, you can see that the Kamioka 2 data is this dotted line. It reconstructs the low energy part. And the IMB data helps reconstruct this high energy part. And there's a way to put that together in like one combined detector and have things be composite. But you'll notice that the composite thing, the combined line, that's that blue solid line, looks different than the gray thing. The gray thing is a simple thermal spectrum. And what this shows is that the 87A data suggests it's not a thermal spectrum. It suggests that it's higher in luminosity, in particular at low energies. And so that is related to how we make sense of the Kamioka and IMB data together. And of course, in this paper on the left, we go into details about that.
Thank you very much. Marianne? And then, sorry.
Hi. You mentioned, how accurately we can measure the position of the supernova with neutrino detectors, but what about the timing information? Because this is very important for gravitational waves. Can
Yeah,
you
that's a great
comment on,
question.
nearby and galactic and nearby supernova, please?
Okay, so let's start with the Milky Way supernova. Actually, let's go, well, I don't think I have the 87A data in front of me right now, but the 87A data showed that the signal lasts about 10 seconds. So there's a little bit of a paradox here. Individual neutrino events can be measured to a time of like nanoseconds. But the entire neutrino pulse itself has a rise time of like maybe 10 to 100 milliseconds, and then a decay time of several seconds. So while individual neutrino events can be measured in nanoseconds, how well we can localize the whole thing depends on the time features in the whole pulse. And that is related to this question here about triangulation timing. And the answer is you can probably only localize the start time to tens of milliseconds. And that is related to the fact that the start time is relatively long, and also the statistics in it are not very high. So that's for the Milky Way. In a nearby galaxy, you would just know that you've got one or two neutrinos. You would know it within some seconds, and that's the best you could do. So this will never have the precision of gravitational wave detections, I'm sorry to say. Does that answer your question?
I think Marianne has a little bit of a follow-up.
I think knowing the time of the neutrino within 10 milliseconds for gravitational waves, this is super important because it gives us the T0, where to look for in our data.
Yeah.
This is super important.
Yeah.
This 10 milliseconds precision, I think, is good enough in some sense for us.
Okay, Sergey?
You mentioned the early supernova warning. Would it be possible, and how long before the Betelgeuse explodes will we know about, that it's about to happen?
Yeah, great question. Okay, so there's two possible warnings we can have. Let's start with the kind of easy one, which is the neutrinos are emitted from the protoneutron star promptly. And then, like I said earlier, the shock takes some time to go through the envelope and then for the light to get out. So the neutrinos can be seen before the light by an amount that varies between like 10 minutes and days, depending on the mass of the progenitor. That's an example of an early warning that once we see the neutrinos, we know that we should get every electromagnetic telescope looking at the Milky Way. By the way, I want to quickly remark, many people assume that the astronomers are watching the Milky Way all the time. And I have bad news for you. That's basically the one place they don't look. Almost all large telescopes are pointed outside of the Milky Way. Only some smaller telescopes like Assassin here in the lower left are actually routinely surveying the entire Milky Way plane. And then, now your other question, I think, was about the pre-supernova emission. Is that correct?
Yeah. Basically, if we have any time before we know that core collapse is about to start, so we can turn the gravitational detectors on.
Yeah. Okay. Okay. So the pre-supernova emission from the massive star itself that comes out some days to hours in advance of the core collapse. So that's when it really still is just a star. This is this Odrvolik et al. Paper from, I think, 2004. Unfortunately, that technique only works for very nearby sources, like a couple of kiloparsec, but it's a fantastic idea.
Any other questions? Yeah, Christine? Christine's in the back, and then Irene? Yeah.
Hi, thank you very much for the great talk. So I just have a question about whether or not like sort of the timing, or like the time of arrivals of the neutrino matters. So like, is there like a time series saying like, you know, we have a small burst of neutrino and then at the explosion we have a larger burst of neutrino. So we kind of, instead of seeing one peak, we kind of see like a multiple peak. Sorry, this might be a naive question because I'm not quite sure what a neutrino signal looks like.
Okay, yeah, I should have done a better job just showing a neutrino time profile. But what it looks like roughly is, let's imagine you had infinite numbers of events. What would happen is you would see the counts go up, and then, you know, reach some sort of plateau and then decay very, very slowly. So with a finite number of events, you see that sampled. So it's just like nothing, 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 an event, nothing, 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 an event, nothing, 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 an event. So it's a Poisson process. It's not a continuous wave situation like gravitational waves. So it's just more and more counts at the beginning, and then fewer and fewer and fewer counts. And you would just reconstruct the time series from that. And like I said, what that should look like is a fast rise, sort of a plateau, and then a kind of a long decline. Does that answer your question?
Yeah, very good. Irene?
Thanks for the nice talk. Could you comment a bit more on the fact that IceCube and ChemTreeNet will not pinpoint the position of the neutrino if ever detected?
Yeah, great question. Thank you. So in detectors like Super K, where they're buried deep, deep underground and it's super dark and all of that, and Super K has about 10,000 phototubes for its relatively small volume. And so each neutrino makes a positron or whatever, and it hits like, I don't know, 50 PMTs. IceCube is incredibly bigger, or KM3Net is incredibly bigger, but they also have only about 10,000 phototubes. So it's the same 10,000 PMTs, it's just spread out over an enormous volume. And so the probability of one neutrino event hitting multiple PMTs goes way down. So what happens in IceCube or KM3Net is one neutrino is gonna make a nice burst of light, same as it does in Super K, but it's probably only going to hit one PMT. And so what that means is you can't distinguish that from some local radioactivity that hits one PMT or thermal noise in a PMT. So they can't reconstruct events. In IceCube, you reconstruct events from the fact that, you know, they hit the wall at bing, 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 and it sort of looks like a Cherenkov ring. In IceCube, you're just going to see individual PMT rates kind of fluctuating up and down, up and down, up and down. And collectively, you'll see the total PMT rate eventually go up for a supernova and then come back down afterwards. So they can't reconstruct any individual neutrinos. Individual PMT hits could be radioactivity, could be neutrinos from a supernova. They can't tell. The only thing that they can do is see an overall rise in the noise rate. And so there's no energy information. There's no directionality. They do get good measurements of the time profile, and that in principle would help with this new neutrino triangulation timing. But Earth is just too small compared to the length of the supernova pulse.
Follow up? Yeah, that's fine.
I'm sorry, just another comment. So I'm a bit puzzled because ChemTreeNet has these multiple PMTs inside an optical mode, and the ChemTreeNet Orca is the one that is denser respect to the other one that is looking at
Yeah.
energy, so above the TeV energy. So in that case, probably we will be able to see any kind of reconstruction in position, since the detector has the characteristics that you were mentioning before. Is that
Yeah.
right?
Yeah, let me try to say that a little better. In Super K, one neutrino event might hit 50 PMTs. In IceCube, one neutrino event might hit 1 PMT. But you're right, in KM3net, when you have these clusters of PMTs, there's a possibility that neutrinos could hit 2 or 3 PMTs. That's not enough to do an event reconstruction, but it is enough to help beat down the backgrounds. And that's a paper that KM3net has yet to write, and I look forward to reading it, where they do these semi-reconstructions. Does that answer your question?
Yes, thank you.
Thanks, John. Yeah, Dimitra? I know we're 15 minutes over. There's a lot of interest here.
Hi, thank you for the talk. I was wondering, you mentioned that we could have supernova imposters. So what would that be?
Great question. What is a supernova imposter? Nobody knows, but it seems to be some outburst of the outside of a star that leaves the star basically intact.
Okay. So would that be an imposter only for neutrinos?
So those imposters make an optical signal that's comparably bright to a core collapse supernova, but they leave the star intact and they don't emit neutrinos at all.
Okay. Thank you.
Okay, so in the interest of time, this is wonderful. Tomas, were you going to go ahead, Tomas? I'm sorry.
Thanks a lot, John, for the talk in the early morning hours on your time. I don't want to go into details also because of the advanced time. Let me just comment, because I'm co-author on this Fiorillo paper, which you pointed out. I don't agree with the comments you gave. That's of course, but we would have to argue, and I don't want to do this in the audience here. On the other hand, I must say that this statement that this paper was written after US was out is not quite true. The project was a longer term project and it was ongoing already. And there was an incident that the papers came in a short row. And we actually didn't even want to comment on the one you had written, but we had to somehow include that. Okay, thanks a lot. I heard your arguments and I just wanted to leave the comment that I don't agree with them.
Okay. Okay.
Well, quick comment on that. Thomas likes to talk about this, that he was working on this already with a master student paper. But if you go back and you read the master student paper, it actually has nothing like this that we have. Our paper came out, we sent it to you for comments well in advance of putting it on archive. You did not talk about a master student paper at that time. I went and looked up the master student paper later. It has nothing relevant to this in it. Your paper came out several months after ours, and it does a very poor job of giving credit to ours.
It was not the same topic. We had a different direction of investigating the data. You concentrated on the first half of a second, and our paper is on the full signal.
Hey.
Fortunately, I cannot hear you.
Yeah. Okay. So, John, I just want to say, thank you. This was magnificent, and for you, the time is obscene. We really appreciate this. I mean, obviously there was a lot of interest. We could probably keep you up till dawn, but I'm going to get in trouble if I let that happen. So,
okay, thanks to everybody. Sorry for you not being there in person. I wanted to be there, but United Airlines didn't want me to be.
Yeah, right. Let's thank John. Okay. Who's chair?